Up to now, we've been looking at a bunch of these n series, and we're looking at these n series and see if they converge or diverge or have a finite or infinite sum. And there are some specific ones that we've kind of looked at. So this 1 over n squared is called a basal series, and it happens to have a known sum. We know it's converging, but it happens to have a known sum of pi squared over 6, and that's quite interesting. We have this alternating harmonic series, which has this harmonic series, but it alternates between positive and negative, and it has a known sum of log 2, or about 0.69. And these sums are very interesting, but however, they're not that important. The actual value of the sum is not that important. What's really important, though, is the fact that they converge, and they're very useful when they converge. So we've looked at these S series, or these N series, and we're going to look ahead to where we're going to go with this. So eventually what we're going to do with these N series is we're going to make these other series that look like these ones. And these are actual functions. We're going to make functions with these series. And these series have two parts to them. So I have a function e to the x here. Okay, e to the x happens to be expressed as a series, and this series has two parts. And the fact that it has an x in it and is different than n is key, because we've now paired this n series. In this case, we have factorial in blue in the denominator. That's an n series. But in the numerator, we have these powers of x. And these are just whole number powers of x starting from 0, 1, 2. And we can express e to the x using this polynomial series. Okay, and it goes on infinitely. Same with sine. Okay, we have sine x. We have the n series part in blue. Okay, so the blue part represents the n series. We can generalize it with the sigma notation. And this is something we want to start getting used to reading, the sigma notation. The blue part is 2m plus 1 factorial. So we just have, in this case, 3 factorial, 4 factorial as we increase the n. So there's an n part of this series in blue. But the red part is new. This is a polynomial series. We have these powers of x, and it happens to equal the sign. And these are defined series, and we don't know how we get there, but we're going to build these later. But to build these, we need to understand the parts of them. And there's this n series in blue, and then there's this new part. It's a polynomial series in red. And together with those, we can start defining these more complex functions, such as e, sine, cos, log. And what's useful about these polynomial series is that they are, although they're estimations of these really complicated series, there's a huge advantage here in that we have an e function that we're not really sure how to use add, subtract, times, or divide to calculate. Same with sine. We can't actually use add and subtract, times and divide to work out sine values. Okay? We don't really know what that is. However, these polynomial functions, number one, they are the simplest functions, polynomials. They're just whole number powers. They rely on addition, subtraction, multiplication. And we can use this to actually calculate values of sine. Actually use a calculator to do some kind of calculation and get sine. Before, it was a big black box of how we ended up with sine values of non-exact values. Same with cosine. It's a black box of how do we get to those calculations. But now with these infinite series, we now have some kind of calculation that allows us to get there. Now, these are estimations, but these polynomial series are infinite, and we can get as accurate as we want by using more and more terms of this series. And the fact that we can go to infinity allows us to make this into a perfect function. And now we have a polynomial function, which is our simplest function that relies on addition, subtraction, multiplication, division, to start expressing values of things like sine, where before we couldn't use add, subtract to calculate these things. So this is where we're going with them. And again, they're composed of two parts, the n series part, which is what we've been looking at so far, and this new part, this x series part, which we're going to call a power series. And we're going to stitch those together to be able to make series that represent functions. To look at these functions, we're going to first of all start with the power series part of it. And the power series is a series with an x. It has a base of x, and we're just going to start with x to the power 0, x to the power 1, x squared, x cubed, and go on infinitely with that. And that power series actually happens to be an infinite geometric series, and we can work it out, but this power series is defined as the function 1 over 1 minus x. So what ends up happening is this series works out to be this particular reciprocal function. Now, it has some limitations, but the limitations are going to be based on the fact that this needs to converge, which means that the base, or x, has to be between -1 and +1. So we're going to look a little bit closer at this.